So welcome everyone to the ECOPRO online seminar. Today we have the pleasure to have Qizhong Lin from Fuzhou University telling us some recent progress on Ramsey-Turán problems. Qizhong, so yeah, it's all yours.
Okay, first I would like to thank Hong Liu for the invitation, and also thank Jun King for the help. So today I will introduce two new classical Ramsey-Turán densities, and this is a joint work with my student Xinyu Hu. Okay. We know from Ramsey theory, we know that for any key integers P1, Pk, there is a minimal integer now called Ramsey number, such that any k covering of edges of the complete graph Kr contains Kpi in the ith color for some I. And we know the diagonal Ramsey number can be bounded as follows, where the lower bound due to Spencer was obtained by using Lova's local lemma, and the upper bound due to Sa improves the previous best result by column. So just 1 week ago, we know that Campos Ito give an exponential improvement over the upper bound. Motivated by the Ramsey theory, Turán posed a problem to determine the maximum number of edges of a KP-free graph. In particular, Turán proved that the balanced computer puppet graph, now called Turán graph, is a unique extremal graph which attains the maximum number of edges among all n vertex KP-free graph. We know that Turán graph have very large independent sets, roughly size linear in n. So it is natural to ask for the maximum number of edges without a large independent set. And this leads to the study of Ramsey-Turán type problem mentioned by Erdős and Sós. We shall give some definitions. We say that G is KP1, KPK free. If there exists a K edge covering of G with no monochromatic copy of KPI in the ith color for I from 1 to K. And the Ramsey-Turán number is defined as that the maximum number of edges of n vertex graph G, which is KP1, KPK free, and independent number at the most n. Note we see if the Ramsey number n, if the number n is greater than the Ramsey number, and then such a graph does not exist. So indeed, we usually consider the case when m is little o n. Yeah. The Ramsey-Turán density is defined as follows, and indeed it is a double limit. The Ramsey-Turán density is well understood for the one color case. In particular, Erdős and Sós obtained the density for all the other case. And for the even case, it seems much harder, apart from the trivial case K2. As an earlier application of the regularity lemma, generally showed that low 4 is at most 1/8, and there is no non-trivial lower bound until Balabas and Erdős give a geometric construction. And finally, Erdős Ito determine all the even case. Now, let us take a look at the lower bound for the one color case. The following is the Erdős graphs, and it tells that it is a graph which is triangle free with independence number little o(n). Yeah, and we know there are indeed many other triangle free graphs with small independence number. In particular, a celebrated result of Kim gives a tight bound of the order of the independence number. And so and then let me introduce the following definition, that is the Balabas-Erdős graph, which is constructed on the high dimensional sphere. In particular, the Balabas-Erdős graph is K4 free with independence number little o(n), and each vertex has a degree roughly n4, and the subgraph spanned by each xi is triangle free with edge number little o(n) square. One can see that Liu Hong and Ito for a class of the Balabas-Erdős type graphs on the high dimensional complex sphere, and which can be used to give all rational densities for generalized Ramsey-Turán densities. And now we have the lower bound for the one color case as follows. For the other case, we first have a balanced complete p-particle graph, and in order to destroy the large independent set, we put an Erdős log graph, into each partite. The situation for the even case is much different. The first non-trivial case is the Balabas-Erdős graph, and in general, we should add a p-2 part to it, and any other pair of distinct parts are completely connected, and we put an Erdős graph into each of these p-2 parts, and note that they are not balanced. However, it is much more difficult to determine multicolor Ramsey-Turán density. Erdős, Ito, Erdős, Hajnal, Simonovits, Sós and Szemerédi proposed the following problem. Indeed, they made the following conjecture. Provided the independence number is much smaller, then we can obtain the density as desired, just obtained by Kim and Liu, and in 2019. Upon these results, they proposed the following conjecture for the even case, i.e. the Ramsey-Turán density low 3 2Q. And however, for the two color case, we only know four values as follows. No more values known. And we are between two new classical Ramsey-Turán densities, and moreover, we can say that the corresponding asymptotically extremal structures are weakly stable. And our results are as follows. And the weakly stable property holds means that any of the corresponding extremal graph can be obtained from the other extremal graph by deleting or adding a little o n square edges. And Erdős Ito asked whether the asymptotically extremal structure for the Ramsey-Turán problem is weakly stable. The answer is yes for the one color case. For the two color case, we only know that the property holds for the known four Ramsey-Turán numbers. Now, let us take a look at the lower bound for the two color case. For the order case, we first have a balanced complete RPQ minus 1 parted graph, which is KP KQ fluid. And then we destroy the large independent set by putting a red Erdős graph into each partite. Here, the red color corresponds to KQ. We always to find a blue KP and or a red KQ. For the even case, it seems a little different. We first have a balanced complete RPQ parted graph, and then we embed a blue extremal graph for the Ramsey-Turán number involving KP in the last class, and embed a red Erdős graph into all the other classes. And we can see it is KP K2Q3, and so the lower bound followed. In order to we focus on the upper bound, and to this end, we need more constructions and definitions. The following is the generalized Balabas Erdős graph defined on T classes, in which some pairs are joined completely, and the others are joined by a Balabas Erdős graph. Indeed, Erdős Ito showed that there exists a sequence of dense GBE graph. Such a graph we always call the generalized Balabas Erdős graph, or shortly GBE graph. And Erdős Ito showed that there exists a sequence of dense GBE graphs asymptotically extremal for the Ramsey-Turán number. In order to find the desired complete graph, we need to find a generalized complete graph in the colored and weighted reduced graph, and in which each marked vertex always contributes two vertices to the desired complete graph. And the following is a generalized complete graph, defined by Erdős Ito. So for a colored and weighted complete graph KT omega, in which each edge is assigned with weight 1 or half. And we know the edge density of the weighted complete graph KT omega, GKT omega, takes the maximum value over all U. Yeah, over all U. One can refer the KT omega as to the reduced graph of the corresponding generalized Balabas-Erdős graph. We also can see the following relation, where A is the weighted adjacent matrix of the weighted computer graph. That is corresponds to the general Balabas-Erdős graph. We can see in the following that such a graph always is dense because the maximum is always attains in the internal domain. Yeah. So now we have the following relation. The following lemma tells that the canonical colored generalized Balabas-Erdős graph does not contain a monochromatic KL if and only if the corresponding colored weighted computer graph does not contain generalized KL in the same color. And here the canonically coloring means that all edges in a class have the same color, and all edges between any pair of classes also have the same color. In particular, a vertex of a generalized KL is marked with the color K, contributes 2 vertices to the KL in the colored generalized Balabas-Erdős graph. And the following result tells that there exists a sequence of dense generalized Balabas-Erdős graph asymptotically extremal for the Ramsey-Turán number. And in particular, we know that the Ramsey-Turán density low PQ equals the density of the computer graph, weighted computer graph KT omega. The edge density here KT omega corresponds to the weighted corresponds to the generalized Balabas-Erdős graph. Now we have a simple lemma, and this lemma tells that if a graph Bn has roughly the number of edges as a kk plus 2 free Turán graph, and A is a subset with little o n square edges, and the subgraph Bn minus A has roughly at most the number of edges of a kk plus 1 free Turán graph. Then indeed we can see that the number of edges of the subgraph of Bn minus A this lemma tells that if a graph Bn has roughly the number of edges as a k plus 2 free Turán graph, and A is a subset with little o n square edges, and the subgraph Bn minus A has roughly the number of edges of a kk plus 1 free Turán graph. Then indeed we can find that the subgraph Bn minus A has roughly the number of edges as a kk plus 1 free Turán graph. From this proof, and we can also have the following lemma. Indeed, the idea is, I think it is are very similar. Yeah, this can be used to consider the structure of the generalized Balabas-Erdős graph, BNT. Yeah. In order to to obtain the upper bound for the Ramsey-Turán density, we also need the following result due to Brown, Erdős, Simonovits. This result tells that the optimal weight distribution of vertices of a dense weighted Kt omega is attained when all the weighted degrees are equal. Indeed, the proof is direct by using the Lagrange method. This result and the following lemma always can be used to prove the upper bound for the Ramsey-Turán density. In particular, the following lemma 14 tells that if in a dense Kt omega, each vertex is incident to at least lambda half edges, and then we can upbound the density of the weighted complete graph Kt omega. Furthermore, if there is no lambda regular graph on T vertices, and then the inequality is strict. Okay. Now let us sketch the proof of the density low 3/6. The lower bound is clear from the above construction, and so it remains to show the upper bound. This lemma gives an upper bound for the Ramsey-Turán density. In order to show the upper bound, we need to force out some special structures. For example, we need to find some disjoint half C file or K4, half K4, or half triangle, or independent edges. Let us see the proof. To show the upper bound for this density, we may assume that all the other edges are full, and we can show that the half C file is a dense structure. Moreover, indeed, why? Indeed, the density attains the maximum in the internal domain. So this structure is dense, and also all the other K4, K3, K2, and other vertices are also dense, and so we can see that W is dense. Therefore, from lemma 13, we just know, and we can see that all the weighted degrees are equal, and so from a simple computation, and we can find the upper bound for the density. The following lemma 16 tells that a red-blue edge coloring of K5 with no monochromatic triangle should be a pentagon-like coloring. That is to say that the subgraph induced by all red edges or blue edges are the cycles of length file, C file. To show the upper bound of the density low 3/6, we may assume that the generalized Balabas-Erdős graph BNT is the corresponding dense asymptotically extremal graph with this canonical coloring on T classes. We say that a vertex of Kt omega is blue if all edges in the corresponding set XL for some L are blue, and a red vertex is defined similarly. Clearly, any blue vertex of the weighted computed graph KT omega cannot incident to a blue edge. Otherwise, we can find a blue triangle. Here, we ask for that the colored generalized Balabas-Erdős graph contains neither a blue case triangle nor a red case 6. So we shall separate the proof mainly into two cases. First, we may assume that there exists a blue vertex X. Then we can apply lemma 9, CN3, lemma 2, and 11 to obtain the distance of the GBE graph and HN33 is little o n square. And we can see that only when t equals 6, such a generalized Balabas-Erdős graph, GBE, BN6, can achieve the Ramsey-Turán density 5/12. So we may assume that all vertices of KT omega are red in the following. And in order to complete the proof, we should force out some special properties and structures. In particular, we should show the following fact. For example, t is less than 14, no more than 14. Also, we need more facts and consider all cases when t less than or equal to 14. For this case, for the low 3, 6, it seems not so complex. However, for the condition of the low 3, 7, it is much more complex. Also, we can show that the weakly stable property of the corresponding Ramsey-Turán number hold. To this end, it suffices to show that for any sequence of asymptotically extremal graph, the distance between the GN and HN33 is little o n squared. Is little o n squared. To this end, we first apply a result of Bilog, Liu, and Sarif-Zadar to obtain a partition of VGN, so that every subset Y of size at least radical delta n contains an edge of color K. And then we apply the regularity lemma to obtain an Ibition regular equitable partition, which refines the previous partition. Consequently, we have a weighted and colored reduced graph H omega 0. And in particular, we color a vertex VI by color K if only if the class VI is contained in UK. That is to say, the vertex VI is marked with color K. Moreover, if the if the k density of a pair VI-VJ is at least a half plus 2 mu, and the VI is marked with color K, then the class VI always contributes 2 vertices to the complete graph KQ. We want to find. Then we can see that the reduced graph H omega contains neither a blue generalized triangle nor a red generalized K6, since GBE graph doesn't. In order to show the weakly stable property, we have the following definition. We define a weighted and two-colored Turán graph FM6 as follows. In particular, the edges of W is assigned with color 1, and all the edges in other parts and that join W6 receive color 2. And the coloring restricted on the other 5 parts is canonically fat pentagon-like coloring. And then we can see there is a number of edges of the reduced graph H omega 0 roughly equals 5/12 m squared. Furthermore, the number of edges of H omega 0 equals 5/12 m squared if only if the reduced graph H omega 0 isomorphical isomorphic to the weighted and colored Turán graph FM6. And from this observation, and we can see that the distance between H omega 0 and FM6 is little o m squared. And here, this graph FM6 can be referred to as a reduced graph of HN33 by deleting the little n squared internal edges of the 6 classes. And so we can see that the weakly stable property holds. The situation for the Ramsey-Turán density low 3/7 is much more complex. We need to deal with many cases. Yeah. First, we need a definition of the calligraph. We call red-blue edge coloring of the complete graph of order 3k minus 1 a nice coloring if and only if VI-VJ is in blue. If VI-VJ is in blue, if and only if IJ belongs to the calligraph gamma k. And we can see that if k equals 2, then it is a pentagon-like coloring as above. And for the case when k equals 3, it is an octagon-like coloring. We can see the graph as follows in figure 1. This blue graph is a calligraph gamma 3. We also have the following simple lemma. Here simple means that the proof is direct. We have that if percent is a red blue edge coloring of K8 containing neither a red K4 nor a blue K3, then percent must be an Erdős-like coloring. Similarly, in order to upbound the Ramsey-Turán density low 3, 7, we need to force out some special structures. For example, we need the half complement of the calligraph gamma 3, half K5, etc. The proof is similar. So there are still many details. For example, we can see that if the generalized Balabas Erdős graph that is a dense asymptotically extremal graph of the corresponding Ramsey-Turán number, and then we can see that T cannot be greater than 18, and many other facts. For example, if X is a subset of size 4 and X contains no red K3, then X contains 2 independent red edges, etc. In particular, for T equals 10, we have the following property. For example, if K10 omega contains 3 independent half edges, then all the other edges must be half. So many details here. Similarly, the weakly stable property corresponding to the Ramsey-Turán number or the Ramsey-Turán density low 3, 7 also hold. So I think I will not say about the details now. Let us have some open problems. In particular, it is wide open for the Ramsey-Turán density of the low 3 Q when Q is greater than or equal to 8. Moreover, another problem is to determine the Ramsey-Turán density for any sufficiently small data. Similarly, it is well understood for the one color case. However, for the 2 color case, we only know 3 values: low 3, 3 data, low 3, 4 data, low 3, 5 data. From the construction of the low 3, 6 data by Kim and Liu Hong in 2019, they proposed the following conjecture, and the construction is as follows. Here, the graph F and D is a graph that is n-vertex D-regular triangle free and with independent number D, F and D. F and D. Moreover, from the construction of the low 37 data, we believe the following as an end, let us pay some attention to the Ramsey-Turán density for the non-complete graphs. For the definition of the arbosity of H, it is the minimum integer P such that VH can be partitioned into P over 2 sets such that each VI spans first. And if P is order, then the last set spans an independent set. Erdős proved that low H should no more than low P. And in particular, the inequality is sharp for order P. Especially the Ramsey-Turán density of the complete tripartite graph is known. When M is greater than or equals to 3. However, the case for even P is more harder. Even the simplest case when H equals to K 2, yeah. And we do not know if the following hold. Okay. Thank you very much.
Okay, let's first thank Qizhong.
Okay, thank you.
Any questions?